Hi students, this is Mr. Yao. Today we're going to talk about 7.5 where we'll learn about segments inside a circle. But before we do that, let's actually review factoring because we're going to use it for this lesson. First question, x squared minus 10x plus 24. You can choose to use factor by grouping or box method or the cross method, any of these, but for a question simple like this, and when I say simple, I mean when you see the leading coefficient is just a 1, we can actually do something slightly easier. If the leading coefficient is just 1, that means each parenthesis is just going to get 1x. Then you're trying to fill in the blank, the space, with two numbers that adds up to negative 10 and actually multiply it to be positive 24. And the numbers we have is negative 4 and negative 6. So put in negative 6 in the front, negative 4. The order actually doesn't matter. You can put negative 4 in the front, but that is already our answer for number 1. X minus 6 times x minus 4. Next, number 2. For this one, I'm actually going to use the cross method. Hopefully you still remember how to do that. On the top, we're going to put the A and the C. Remember to carry the sign. So it's 8 times C. 6 times negative 12, that's negative 72. On the bottom is the middle number, which is a 1, since there's no number there. We're trying to find two numbers that multiply to get negative 72 and adds up to a 1. The two numbers will be negative 9 and 8. Don't forget to write your fraction line. Next, we're going to put things on the top. It's going to be the leading coefficient with an x on the top. So 6x on the top. And whenever we see a fraction, we got to actually simplify them. That's going to give us not 4x. That's going to give us 3x over 4. On the left side, 6x over negative 9. That's going to be 2x over negative 3. So the parentheses, 2x over negative 3 is going to be 2x minus 3. The right side, 3x plus 4. That's from the fraction on the right side. That's number 2. Number 3. This time we're solving it. You can still choose to use either the cross method or the box method, but if that's the case, you can actually do a plus 0x so that you actually have a b, which is 0. However, this comes from the formula a squared minus b squared. So if you notice, for x squared, that's a perfect square. 81, that's a perfect square. That comes to a plus b times a minus b. And if you forgot how to find the a and b, the a is basically the square root of 4x squared, which is 2x. And the b is the square root of 81, which is 9. So I'm going to put them in two separate parentheses, 2x plus 9, and the other one is 2x minus 9. That's equals to 0. Then we need to solve that equation. To solve an equation, we're going to set each part to 0. That part is 0, and that part is 0. So 2x plus 0 equals 0, plus 9 equals 0. After solving, x equals negative 9 over 2. And 2x minus 9 equals 0. After solving, x is going to be a positive 9 over 2. That's number 3. Number 4. We're going to do our cross. On the top is the 2 times the negative 3, so negative 6. On the bottom is a 5. And the pair of numbers we're trying to find needs to multiply to get negative 6 and needs to add up to a 5. That's going to be 6, negative 1. On the top of the fraction, we're going to put the leading coefficient with one variable, so 2 and x, so 2x, 2x. The left fraction can be simplified as x over 3. So final answer, x, well, not final answer, factoring, x plus 3 times 2x minus 1 equals 0. Now it's time to actually solve. We are going to set each parenthesis to 0. X plus 3 equals 0 gives us x equals negative 3. And 2x minus 1 equals 0 after solving gives us x equals 1/2. These are review for factoring. Now let's actually get into today's lesson. First, segments of chords theorem. If two chords intersect in the interior of a circle, then the product of the length of the segment of one chord is equal to the product of the length of the segments of the other chord. That actually sounds like a tongue twister. So let's actually dissect what it actually means. So we have two chords, which is the A, B, and the C, D. They both cut each other into two parts. So this theorem is basically saying one on the first chord one part times the other part is the same as on the other chord, one part times the other part. So in this specific layout, that's going to be EA times EB. So EA times EB is the same as EC times ED. That is segments of chords theorem. We're going to talk about the plan for proof after we talk about two examples. So first, example 1. We have two chords. One is being cut into 6 and x plus 2. So we're going to multiply them together. 6 times x plus 2. And the other chord is being cut into 9 and x. That's the two parts, so we're going to multiply them together. And the first chord and the second chord actually equal to each other. Now it's time to solve that equation. 6x plus 12 equals 9x. 3x equals 12, so x equals 4. That's example 1. Example 2. There's a typo. It shouldn't be MJ, it should be ML. So this one, same thing. If you look at the chord ML, that's being cut into x plus 2 and x plus 1. So we're going to multiply them together. X plus 2 times x plus 1. And the other chord, KJ, that's being separated into x and x plus 4. We're going to multiply these two together, x times x plus 4. Now it's time to distribute. We're going to get x squared plus 2x plus x plus 2 equals x squared plus 4x. X squared is gone. The left side is 3x plus 2, the right side is 4x. So after simplifying, x equals 2. However, we're not fully done. This question is actually asking to calculate ML and JK. ML, if you look at it, it's x plus 2 with an extra part x plus 1. So x plus 2 plus x plus 1, which is 2x plus 3. Plug in the 2, that's going to give us 7. Then we're going to do the same thing with JK. So it's x plus 4, which is 2x plus 4. After plugging in, that's going to give us an 8. That's example 2. Now let's go back and have a look at how we can prove this theorem. So EA times EB equals EC times ED. Like I've emphasized on before, whenever we're actually trying to prove circles, a lot of time we're going to use triangles to prove. So in this case, we're going to connect AC and BD to actually make up some triangles. And of course, these two doesn't have to be the only triangle we use. We can also choose to connect AD and BC. That can give us another set of triangles. So for this, we can see there are two triangles, AEC and DEB. They don't exactly look the same. So I said we're going to use triangles to prove. If we can't use congruent, that means we got to use triangle similarity. So that kind of identified these are the two triangles we're going to try to prove. So AEC and DEB. And this is, again, backward thinking. We're trying to see what we're trying to get to and figure out the process. So we're trying to prove EA times EB equals EC times ED. If you look at them, EA is here, EB is on the other triangle, EC is on the first triangle, ED is on the other triangle. We haven't ever proved anything with multiplication like this. However, if you actually are trying to prove triangle similarity, by the definition of similarity, we can actually have a similarity ratio. And if that's the case, we can actually try to change this multiplication into a ratio, which would be EA over ED equals EC over EB. You might be wondering, wait, why is it like EA over ED? Because if you think back, if you think the other way, when you actually try to cross multiply this open, EA is corresponding with EB. That's the left side. So diagonally, EA and EB needs to be set in the right place. Then EC and ED, of course, they're also diagonally crossed, and they multiply together. That's cross multiplication. So this is what we're trying to get to. And if you look at it, EA and ED, they're actually corresponding, EA and ED. Then EC, which is right here, corresponding with EB. That actually comes from our triangle similarity. So now it's time to prove the triangle similarity. We can see there is a vertical angle right there. So that's already one pair of angles. Now we just need another pair of angles. Because we can't exactly use side to prove, since our sides are basically right here, We can't use side, so we gotta use angle, angle. That's already one pair, we just need another pair. I'm gonna draw an arc, see if you notice anything. I'm gonna highlight this arc BC. I could also choose to highlight arc AD. I'll do that in a bit. But if I highlight that arc BC, if you remember what we learned in 7.2, we said if an angle is an inscribed angle and is facing an arc, there's another inscribed angle that's actually facing the same arc, then these two angles must be the same. And that is called same arc theorem. Same arc theorem, because they are facing the same arc. So angle CA, measurement of angle CAE, I'm just going to use the enter letter E, is actually the same as measurement of angle CD, because they are facing this same arc. So now that's our other pair of angles. So we have angle, angle. We can prove that triangle being similar. They can form the ratio. That's definition of similarity. Then from that ratio, we do multiplication property that can get us what we actually want. So, of course, you can also choose to do the other one. I can highlight AD, then that means it would be these two angles. Choose a different color. I can highlight AD, then it would be these two angles that are facing the same arc, so they are actually the same. So that's another pair of angles that you can use as well. That's segments of Chords theorem. Now let's move on. Next, segments of Secants theorem. Two secant segments share the same endpoint outside a circle, and the product of the length of one secant segment and its external segment equals the product of the length of the other secant segment and its external segment. So the first graph is just kind of showing you where the external segment is. It's actually just talking about the part that is completely outside the circle, which is also on the secant line. And of course, the specific one is actually talking about this one. And we're going to form the same kind of thing. EA times EB is equal to the EC times ED. The difference, well, that saying is exactly the same as the previous one. However, the difference is the previous one is just two different parts of the same chord. But this EA times EB, so it's external times the whole thing, which equals to external times the whole thing. So that is segments of secants theorem. External times the whole thing. We're going to do the same thing. We are going to do some practice first. So external times the whole thing. The external is on the top is x plus 3. The whole thing is x plus 3, then plus 13. So x plus 16. That is on the top. On the bottom, this line equals to x plus 2 times the whole thing. So external, which is x plus 2. The whole thing is x plus 2 plus 17. So x plus 19. And of course, in this case, we are going to need to distribute so that we can solve it. Distribute the top, that's going to be x squared plus 19x plus 48, which equals to x squared plus 31x plus 38. The x squares are gone. The 19x and the 31x, that's going to be a 12x on the right side. 48 minus 38, that's going to be a 10. Actually, that's not 31. It's actually going to be 21, so it's 2x equals 10, which after solving, x equals 5. That's example 3. Example 4. We have this external one, again, 3 times this whole thing is going to be 3 plus x plus 2, x plus 5, which equals to the bottom first, x plus 1, and then the whole thing is x plus 1 plus x minus 1, which is 2x. So set them equal to each other, now it's time to solve. 3x plus 15 equals 2x squared plus 2x. And start solving that quadratic. 2x squared minus x minus 15 equal 0. We can use factoring to solve. 2 times negative 15, that's negative 30. On the bottom is negative 1. And left side and right side, we have the combination that multiply to get negative 30, or adds up to negative 1, that's going to be negative 6 and 5. And of course, on the top, we're going to put the leading coefficient with an x. So 2x, 2x. That is going to be negative 1/3, 1x over 3. So time to put in the parentheses. That's going to be 2x. Actually, not 2x. That's 1x. So it's going to be x minus 3 times 2x plus 5 equals 0. X minus 3 after solving is going to give us x equals 3. 2x plus 5 after solving is going to give us x equals negative 5 over 2. Of course, this is talking about length, so we can't exactly use a negative number for length, which is why negative 2.5 doesn't work, only a positive 3. That is example 4. Next, we have one last kind. So in angles, we talk about when the intersection is inside a circle or outside circle. Here the same thing. We also could make that line slightly touching the circle. If you remember, that is called a tangent line, which is why this theorem is called segments of secants and tangents theorem. So let's actually start using it. That's going to be EA squared equals EC times ED. So this case, if you think about it, we just don't have EB. However, if we do, EB will be like around here, which is very close to A. So when we actually make A into a tangent point of tangency, all of these are actually forming that relationship. Next, example 5. So same thing, external times the whole thing, 1 times the whole thing is going to be 4, which equals to the outside tangent segment squared, so x squared, which means x squared equals 4, square root both sides, x equals, I know it's supposed to be positive and negative 2, but we can't have a negative distance, that's why I'm going to keep the positive one, so x equals 2. Example 6. We have 16, that's just the tangent segment, so 16 squared. Then we have this x, and the whole thing will be x plus 8. So that equals x times x plus 8. And to solve that equation, x squared plus 8x, we're going to minus the 16 squared over, so minus 256 equals 0. That question actually can't be factored. So we're going to use quadratic formula. X equals negative b, which is negative 8. I'm going to write the quadratic formula on the top, just in case you forgot. Negative b plus minus square root of b squared minus 4ac all over 2a. So it's negative 8 plus minus square root of 8 squared minus 4 times 1 times negative 256 all over 2. That is going to be negative 8 plus minus, after calculation, the top is going to be 1088 all over 2. So we got negative 8 plus minus. Simplify that, that actually is 64 times 17, 64 times 17, so it's going to be 8 square root of 17 all over 2, which is going to be negative 4 plus minus 4 square root of 11. And RS is actually just x. But since it needs to be a positive number, we are just going to keep the positive, so negative 4 plus 4 square root of 17. That is example 6. Now let's go back to actually talk about that proof. This is actually very similar to the previous one. So we're still going to connect AC and BD, and we are going to actually form the ratios the same way. EA over ED is the same as EC over EA again. And if we look at it, the two triangles we're going to identify, because EA and ED must be corresponding. So EA, which is this triangle, and ED must be corresponding. So we're trying to prove these two triangles being similar. AEC and DE. If you have a look, we can clearly see they already share this angle right here, which is the basically angle AEC is the same as DEA, and that is reflexive because it's the same angle. So now we just need to find one other pair of angles. And something special about this is AE is actually a tangent. AE is a tangent. This is a tangent. But AC is a chord. So if you actually recall, we have learned something about that's called tangent and chord theorem. It's basically saying if you have this tangent line and you have this chord that cuts the circle into two parts, whichever part is within the angle that is formed, that angle is half of the arc, which means this angle right here, angle EAC, is actually half the measurement of the arc AC. And if you look carefully, arc AC is actually facing this angle right here, which means that angle is also half of measurement arc AC. So that is actually the same of measurement of EDA, which is right here. So if you look carefully, EDA is in the second triangle and EAC is the first triangle. So they are actually connected by this arc AC because they're both half of the measurement of arc AC. Now they're the same, so we have second pair of angles. And of course, angle E is congruent to angle E. And with both of these, AA, we can prove the triangles are actually similar. That's the proof for segments of secant and tangent theorem. Now we have one last example. Example 7. EF is a tangent segment. AD, the arc is 140 degrees, which is right here, that's 140 degrees. AB arc is actually 20 degrees. Angle EFD, which is right here, that's going to be 60 degrees. AC, which is actually talking about this little line segments that we couldn't exactly see because it kind of coincide with the circle. That part is 3, and AC is 6. ED is 10. DC is 10. So first, find the measurement of angle CAB. You couldn't tell, CAB is right here. And the arc that angle is facing is arc BD. So measurement of angle CAB is actually 1/2 the measurement of angle of arc BD. And BD is basically AD minus AB. So it's 1/2 measurement of AD minus AB. So we're gonna do, since AD is 140 degrees, AB is 20, so 1/2 times 140 minus 20, which is 60 degrees. That is the measurement of a CAB. Show that a triangle ABC and FEC are similar. We already have a vertical angle right there, and that angle is 60 degrees that we just found out, which actually is the same as measurement angle EFE. So AA, we can prove they are similar. Next, part C. EF is Y and DF is X. We're going to use the previous step to actually form a proportion. So the triangle being similar, that's going to give us AB over FE, just corresponding parts AB, FE is the same as AC over FC. So if you look at it, AB is our 3, FE is going to be our Y, AC is our 6, and DF, actually not DF, FC is going to be X plus 10. So we got 6Y, 3X plus 30. After solving and simplifying, Y is going to be 1/2 X plus 5. That's part C. Part D. Use a theorem to write another equation involving both X and Y. If you actually look at it, this FE is a tangent line, which is something we just learned in this section. We have a tangent line, we have a secant line that can form some kind of relationship. So it's going to be y squared, the tangent part squared, equals to external, which is just x, times the whole thing. So x times x plus 6. And if you recall, in quadratic unit, we actually have something like this. We have two equations. We can actually put them together to solve. So now it's time for E. My y is 1/2 x plus 5. So it's got to be 1/2 x plus 5. Have another 1/2 x plus 5 equals to x squared plus 6x. So we actually got 1/4 x squared plus, that's 5 over 2x with another 5 over 2x. So 5x plus 25 equals x squared plus 60x. I'm going to multiply both sides by 4. So that is gone. That's 20. That's 100. That's 4. That's 64. So we will get, after simplifying, move everything to the same side, we're going to get 3x squared. That plus 20x, move over to minus 20x from 64. That's got to be plus 44x. And minus 100 equal 0. So after solving, x actually is going to be 2. And if you actually put it back in for y, y is going to be 6. For f, now we're trying to find CE. So CE is actually part of BE, which is the chord. You look at the two triangles, EF compared to AB, that's like twice. So that means EC compared to CB must also be twice, because it's the same as FE over AB. That's the same ratio, which is 2. So which means I can actually just call this 2x. The other one is x. And we're going to have 2x times x, because that's the chord. It's actually the same as 6 times 10. So after solving, my x is going to be 2 square root of 30. And that's part F. That is everything for 7.5. Thank you.